The daily growth rate of the population of a colony of insects. Okay, let's introduce a variable, shall we? Let P I know we like to launch into equations, and it would be quicker probably, but if you're going to talk about variables, you need to know what they are. If that's the population of the colony of insects, the growth rate is 10% of the excess of the population over 1 point. Wow, okay, that's a bit of a mouthful, isn't it? So let's just stop for a second. 10%. 10%, I can do 10%. This is a growth rate, right? It's going to be 10%, 0.1 of something, okay? What's the something? Morning. The excess of the population over that, okay? So there's the population, right? And based on this, it's saying it's higher than that. It's higher than 1.2 times 10 to the 6. What's that? 1.2 million, I guess, okay? So the population's always bigger than that, and it's growing in relation to that. So therefore, you've got P, right? And you've got this 1.2 times 10 to the 6 is 1.2 million figure, right? We want to know what the excess is of the population over that. Well, that's just the difference between these two numbers, right? Which one did we say was bigger? P is bigger because it's an excess over it, right? So therefore, you're going to have P minus this, not the other way round. Okay, is that all right? So this is P minus 1.2 million. That's the excess, right? And so the growth rate is 10% of the excess. There we go, okay? You can see a lot of it's just down to interpretation of the language. At t equals 0, the population is, and they give you a number. $2.7 million. We could have just as easily said P naught, but it doesn't matter. Okay, determine the population after 3.5 days. When t equals 3.5, what's the population? And sketch the curve of the population against time. All right, now, you have a look at all of this and you think about how am I going to put this all together. Clearly, at this point here, I need some kind of equation for P that I can stick 3.5 into, and then I'll get a value, okay? Now, because you've got dp on dt, some of you might think, oh, I suppose integration might be a natural way to think about how to go from dp on dt to p. That's not a bad thing to think. However, being that we know, it says it's 10% of the excess of the population, this is proportional, right? This kind of thing here, this relationship, we know, we have a very, very good idea of what kind of function p is likely to be, even if we don't know the exact numbers, okay? So think about this. You only have a few equations to model this kind of exponential growth, right? And it is growth, so that already knocks out, morning, that already knocks out your decay equations, right? So for example, this guy, he's out, right? This guy, also out, right? So it's going to be neither of those. If it's going to be increasing, it's either something like this or something like this, or alternatively that weird one we saw before, which was something like, I don't know, a on 2 plus negative. Something like that, okay? Now, the reason why I lean towards one of these is because you have a look at this form here, right? If you went and had a look, when we did this, right, we differentiated to try and look at what the graph would behave like, right? You didn't get back this simple proportionality thing here. You got quite a different equation, right? So that's why even though this will give you a kind of exponential growth, it's not going to be the one that I'm interested in because the differential equation doesn't match that, okay? So therefore, it's going to be one of these. Now, being that we know what differential equation matches to this, right? It's just a simple, you know, dp on dt is just proportional directly, right? That's what leads you towards this, okay? So, just stop there. This is tricky. I wrote this all out so you could see what's going on in my brain, right? The question doesn't hold your hand at all. It just says, figure it out, right? And the part of the reason why is because when you're in exponential growth and decay land, okay, you know it has to be one of these. There's nothing else that's going to match this kind of differential equation. So they're expecting you to be able to recognize that. Tuner students, not so much. They'd probably actually give you an equation and then say, all right, show that this matches, this satisfies your differential equation, which is why in that very first set of HSC questions, that's often your first, part A. Show that this satisfies this, and then off you go. Okay? But Extension 1 students, you should know these, and you should be able to work out, you should be able to deduce which one of these is going to fit this situation best. Okay? So if I have this situation here, okay, consider what are the pieces of this thing? Do you remember how this thing works? You've got the normal exponential kind of shape, right? But it's been moved up C units, right? So something like this. Thereabouts, okay? Now, think about what you know about this thing, right? There's always this number here, 1.2 million, that you're always above, right? And you're changing in relation to that, okay? Therefore, in terms of this piece of information and this graph, where is it most likely to be? What is it most likely to correspond to? Where's the 1.2 million? It's probably the asymptote, isn't it? Population equals 1.2. Because the question is assuming that you're always going to be above, just there, okay? So that's what you're proportional to, that distance in there. That makes sense, okay? So therefore, I can think about this guy. If I, for instance, just suppose it's equal to AE to the KT plus this, okay? I can actually already sort of work out from this, is it going to fit my differential equation? Have I made a good guess? Okay? Because here, I can say, well, what's dP on dt? What's it equal to? Well, yep, you got chain rule there, so the k comes out the front. K, A, e to the kt. What happens to this constant? Just disappears, okay? So now if I want to turn this back into a differential equation of this kind, right? I've got k times, now what is this? It's not p, it's p minus this, isn't it? It's not the whole thing on this line. So I've got p minus 1.2 million. That's a good sign, isn't it? It matches. Now, what's this k? What does that correspond to? It corresponds to the 10%, doesn't it? Okay, your constant of proportionality. So therefore, you can say, well, if this really should be 10%, 0.1, then that should be up here. That's where k should be, right? So you can see how I'm trying to account for the information in terms of what equation I think would match that. Okay, so what I have now is p equals a e to the 0.1, there's my k, plus 1.2 million. Okay, so now I've only got the time variable and this a, which is going to come from my initial condition, which they've given to us here. Okay, so let's pop that in. When t equals 0, you're going to get 2.7 million on this side. You can see what's going to happen here. This is just going to become 1, because e to the naught, right? So times 1 plus that 1.2 million constant that's just floating around. So that's why you get your value of a as, by the looks of it, 1.5 million. There we go, cool. So now, even though they didn't ask us for it, the question kind of assumes that I need my equation for p. So I can state it now as, I'm going to have 10 to the 6 on both terms, aren't I? So I'm just going to check that at the front. 10 million outside of, here's my a, there's the k, and there is the constant. Okay? There you go. Now, after this, you just substitute in. That's all you have to do. I've got t there. I can put in 3.5. You'll get this, 1.5 e to the 0.35. But of course, that part's really trivial, isn't it? Can we go back and think about how do we get to this point? This is the hard point. If you can get there, you're done, aren't you? Right? Okay. You need to be super familiar with your exponential growth and decay equations, right? You can immediately knock out half of them once you know whether it's growth or decay, and that part's not too difficult to work out. Then you want to think about, are there constraints involved? And you judge that based on the kind of differential equation you've got, okay? And suppose you have the advantage of this exercise being all about constraints, right? So that should lean you even more in this direction. But when it's a general question in an exam, or if it's all mixed up, you look at the differential equation and that'll tell you, okay? That'll tell you whether you've got regular exponential growth or exponential growth with some kind of constraint. And then from there, it's just a matter of feeding in all of the information in order to eliminate all of the constants, your A and your C and your K, right? And they will provide you enough information to do that. We were supposed to graph this, weren't we? We were supposed to graph it. It will probably help us to actually work out what this value is, because this will be our point for scale. Has someone got the number there? I think it's like 3 point something million. Anyone? Yep, I'll just go 3.3. Since I've got two significant figures there, so I'm just going to bring two with me. So there you go. Now I've got some points that I can put onto my graph. I've got an asymptote at, where was it? 1.2 times 10 to the 6. So I'll stick that here. 1.2 times 10 to the 6. I know my intercept, excuse me, is 2.7 million. So that should be, well, it should be a bit more than double, shouldn't it? So call that 2.7. And I know that after 3.5 units of time, I'm up to here, which is not all that much higher than here, is it? So something like maybe there. So if you pick a point like this, and that's time 3.5 days. Hooray, it's beautiful. There you go. Okay.